So hi. So since we are in a Russian-speaking country, some of you may be able to read my Twitter handle, and you're going to come up to me after the talk and tell me that I spelt it wrong. And I'll be like, yeah, I know. Yeah. So what are we going to talk about today? Let's take a look at this piece of code. I used to work on DevTools. My primary language was JavaScript, and I was working on code like this a lot in the last 2 years. But 10 years ago, this would be unrecognizable as JavaScript. And there's a lot of stuff going on in this code, right? Like, we've got class syntax, we've got a constructor, and we've got all this interesting stuff going on. How'd that all happen? And I like to start my talks talking about JavaScript being the happy blender of happy fruit. We've got this happy blender with these fruits from other languages, nice, beautiful, interesting ideas that came from other languages, and they all come together in this happy, beautiful way. So, my name is Yulia Startsev, and I am a recent member of SpiderMonkey. This is an image of me at work looking at code. And I joined the team 2 weeks ago. Prior to that, I was working on DevTools. So, what are we going to talk about in this talk? We're going to talk about a very brief introduction to TC39, and then we're going to go and we're going to follow the Nullish Coalescing operator through the specification. From stage 1 to stage 3, we're going to read the spec. We're going to see which issues fundamentally transformed the specification into what became the final specification text. Then we're going to look at implementation details specific to SpiderMonkey, and we're going to do the parsing, and we're going to do the implementation of the behavior. After that, it will be 6:30, and there's just one more talk, and you're free. Kind of. Not actually. You're going to have to stick around for the lightning talks, right? Because Aki's talking. No, she's not. OK. So, a really brief introduction to TC39. We just had the panel, but just as a quick reminder, TC39 is part of Ecma International. It stands for Technical Committee 39 of Ecma International. We take care of several standards, not just Ecma 262, but also Ecma 402, the JSON standard, Ecma 404, and Ecma 414. I forget which one of those is the standard for the Ecma markup that we have, the language that we use to specify, but we also specify that. And we operate via consensus. This is a subject that takes a bit more time to define, so I'm just going to leave you with that, and we may get into that more deeply through the course of this conference. So, as a one-slide summary of our process, these are the stages that we go through at TC39. Stage 0, someone has an idea. Stage 1, the idea is presented to committee, committee makes comments. Stage 2, committee discusses this feature. Should it be in the language? Stage 3, we have polyfills and browser implementations. Stage 4, the proposal is ready to enter the spec, and will enter when we do the cutoff in spring. So, what's our happy fruit? Well, it's going to be Nullish Coalescing. Entering into stage 0, there's nothing really interesting that happened stage 0 to stage 1. The proposal stayed fundamentally the same. The entrance requirements for stage 1 were identifying a champion who will advance the addition. Also, prose outlining the problem and the general shape of the solution that we're going to have. Illustrative examples showing how the new addition would be used in given code. High-level API, discussion of key algorithms, abstractions, and semantics, and identification of possible potential cross-cutting concerns. For example, maybe this implementation somehow interacts with another, not implementation, I'm sorry, proposal interacts with another proposal somehow. Maybe something, there's a conflict there. OK, let's actually dive into what happened at stage 0. Let's look at the proposal at stage 0. We've got it right here in front of us. And one thing that we're going to notice is that it wasn't called Nullish Coalescing at the beginning. It was called Unary Coalescing. At stage 0, the author was Gabriel Eisenberg. And he gives an overview and motivation for this. And we're going to switch over to the browser, and we're going to do a bit of this in the browser, because it's easier to scroll, and there's a lot of information that I want to highlight. So let's do that jump. There we go. So here we have it. And he outlines what his motivation is. One thing that you'll notice is this you may remember from Nicolo's talk, because I understand that he also brought up optional chaining in his implementation. So this is partially inspired by what was going on with that proposal. And what's being attempted here is let's say you've got an undefined value, and you want to set it to some default. If something hasn't been defined yet, we're looking over here. I don't have a very good highlighter. If it hasn't been set, we want to set some default value. If it's a null value, we want to set some default value. But if it's the header text, and the header text is an empty string, we should have an empty string. And if the animation duration is 0, we should have 0 rather than 300. This isn't possible with the OR operator. So this is sort of an adjustment for the OR operator. It's filling a space that the OR operator, you would have to do some extra computation. You would have to do double equals to null, or maybe you want to be even more specific. You do strict equals against null and undefined to make sure you've got the right numbers in there. So this is the motivation that he's given us, and this is pretty great. And actually, in this proposal, they had already done the spec text. This is super small, so we're going to go really big. The spec text was already done at stage 0. So we can see the spec text at stage 0, which is pretty great. So let's just read this. Let's just read this line by line, because it's quite short, and it'll get us into the practice of reading specification texts. So the introduction states that the main design decisions made in the specification are that the right-hand side, so you've got A coalesces B, the right-hand side, which would be B, is only evaluated if needed. So if A is not null or undefined, that value is used, and B is sort of like unevaluated. We also say, as line 2, that the double question mark, the Nullish Coalescing operator, has the same precedence as the OR operator. The third thing that we say is that the right argument is selected if the left argument is null or undefined. So, pretty straightforward. We're going to see that in a little bit more detail when we get into the implementation. But let's now take a look at the modification that happened to the syntax. So let's read this as well. Vocalizing things is a really great way to learn, because then you actually have to put your knowledge into the sentence structure of English, and that really helps understand what's going on. I'm not going to get into details to what these things are actually called. So let's read the syntax. Logical OR expression is a logical AND expression, or it is a logical OR expression separated by the OR operator, followed by the logical AND expression, or it is a logical OR expression separated by the Nullish Coalescing operator, followed by the logical AND expression. Okay, so we've read what the syntax is defined as. Next, let's take a look at the runtime semantics and how that's been implemented here. And let's read that out loud as well. So, let the left reference be the result of evaluating logical OR expression. So left reference, pointing somewhere in memory. Let the left value be get the value of the left value. So we're going to get the actual thing that's inside of there. If the left value is undefined or null, follow this branch. And this branch is let the right reference be the result of evaluating the logical AND expression, and return whatever is the value of that reference. Otherwise, if it is not null or undefined, any other value, return the left value. Pretty straightforward. Okay, so, oops, things are happening. So let's talk a little bit about what those things are. Now, I think the runtime semantics might be a little bit easier to understand, because it's kind of like pseudocode. Like, you can read it and be like, I understand what's going on there. It makes sense. But the syntax is a little bit harder to understand. Like, many of you might be asking yourselves, what is this? What's going on there? So, the great thing about the specification is it tells you how to read it. So if you've, but the problem with it is, of course, it's 1,000 pages long, so it's really hard to find where you're going to read that. Now, this is all in the slides as well, but I'm just showing you the actual documents so you get familiar with them and you can feel like you can go through them yourselves. Here we have an explanation of what's going on there. So we've got a statement return list with this return flag. That's what we're going to call it. It's a return flag. It's an abbreviation that gets expanded into two definitions, statement list and statement list return. So that's one part of it. OK, let's continue on. And I'm just going to go right into the issues that came up at stage 2 rather than going back to my presentation. But this stuff is all there as well. Specifically, let's talk a little bit about what was wrong with that initial implementation of the syntax that we saw. So the syntax was, just to remind you, let's take a look at it again. This was the syntax, right? We've got logical OR expression, logical AND, logical OR, logical AND, etc. Very simple, it's just a one-line addition, but there's a problem with it. Nullish coalescing has poor associativity precedence leading to a counterintuitive behavior. Valdemar is a delegate at TC39 who's been there for almost the entire life of the committee, and he's really great at reading the proposals and making sure that things are correct. And what he's bringing up here is he's saying that, let's take this example, A or B or C or D or E, and what I expect from this is the first truthy variable is the one that's going to be returned. So if A is truthy, then that's going to be returned. It's going to be A. If B is truthy, then we're going to return B. If B is truthy and A is false. And the rest kind of don't matter. And he says what he's describing, what he thinks of is right associative grammar. But the specification as a result of how the specification is written, an artifact of the specification is that this is left associative. So what's the issue with that, right? Well, he comes down to this point and he says, if the nullish coalescing operator and the OR operator are the same precedence, and precedence, for those of you who maybe are lost by that word, precedence means, think back to when you were in school and learning mathematics, and you've got plus and minus and multiply and divide. Multiply and divide have a higher precedence than plus or minus. However, plus and minus have the same precedence, which means that when you see a statement that has both all of those operators, then you calculate the ones that are multiply and divide first, followed by the ones that are plus and minus. And then from that point on, you go from left to right directions. I'm not very good at them. So he says, the problem with this now is that this left associativity is now observable. Previously, this was unobservable by programmers, but now with the introduction of the coalescing operator at the same precedence as the OR operator, it's now observable. This isn't ideal, and there are three possible solutions, which he lists at the bottom. Switch to right associativity for all logical operators, give the nullish coalescing operator its own precedence level, or forbid mixing OR and the nullish coalescing operator without parenthesizing one of them. Now, I've got candy up here. Which one do you think we picked? Have I got any guesses? Which one? Give all one? Second one. Give it its own precedence level. That's one. Any other thoughts? The last one? Any other? Forbid everything? That's a good guess. We actually did two things. We did both the precedence level and forbid mixing. So it was two of them. Actually, I promised candy, so I'm going to throw candy. I'm going to try. I have really bad aim. Oh, that wasn't so bad. That was bad. I'm so sorry if that hit somebody. Okay, cool. So we actually did both. And let's take a look at what that actually looks like in spec text. So here is the updated spec text after they updated it to address the concern that Valdemar had brought up. So what we had before was this single intervention into the spec, and now we've got quite a lot more going on here, right? Now, we're not going to go through all of it. It would take a bit too much time, but I'm going to highlight something because it's going to come up later. And you'll notice over here, we have this thing called nullish. We looked at flags a little bit before, and we saw how if you add a flag to the syntax definition, to the grammar, then it's going to expand into two things. Well, now, what's happening is we've added another flag, and we're doing something really weird, which is this funny thing, which is having a tilde and then nullish. What is going on there? That's really interesting, right? So there's more to these flags. These flags actually determine how these statements expand in more ways. And in this particular case, because what we're trying to do is disallow nullish coalescing from mixing with an OR statement or an OR expression or an AND expression, what this is doing is when you've got the tilde in a spec, it means that make sure that this line isn't present if there is if there is a coalescing expression. If there's a nullish coalescing expression, this is not valid. That's what that's saying, right? All right, so that's the simple explanation of that. Moving on, oops, what did I do? I did something. Next, well, naturally, we get another issue from Valdemar, and he says, please simplify the grammar. And what he says is that this flag, this nullish flag, isn't necessary in order to achieve the behavior that we wanted from the specification. Instead, what we can do is we can define the pieces that we're working with a little bit differently. So let's take a look at how they did that. Oops. So here we are, looking again at the spec text. Also, I forgot to mention, in the introduction, we've changed these lines. We now say that nullish coalescing has lower precedence than OR, and nullish coalescing cannot be immediately contained within an AND and OR. So this is a really nice explanation of what's going to happen over here. So now let's read this out loud again. A logical expression is a logical OR expression or a coalesce expression. So it can be one of those two things. The logical OR expression is defined elsewhere in the spec. We don't see it anymore. It's now gone. But it's defined as it was before, being a logical AND expression, or it's a logical OR expression separated by the OR operator, followed by a logical AND expression. Then it continues. We've got two new things here. A coalesce expression, one other thing. Logical expression is now wrapping these two things, logical OR expression and coalesce expression. The coalesce expression is defined as coalesce expression head separated by the coalescing operator, followed by bitwise the bitwise OR expression, which is defined elsewhere. Then the next line is the coalesce expression head can be a coalesce expression or a bitwise OR expression. That's a mouthful. Nah. So one thing that we can notice is that there's a recursive definition here. Expression head says that it can be a coalesce expression, and a coalesce expression has coalesce expression head inside of it. So the final thing that we're going to look at, and one thing you'll notice is that a lot of additions were made to different parts of the specification, but overall the runtime semantics stayed the same. We are really just looking at how things are being changed in the syntax of things. Okay, so finally, the last issue that I want to raise that shaped the specification is this one. Rename logical expression to short circuit expression. So this one was done by Ross Kiersling. Ross and I were the two reviewers on this proposal. And he noticed that logical expression, in the way that it's being defined now, doesn't really refer to something that we would conventionally consider as logic, unless we're thinking about ternary logic, because the coalescing operator isn't the same as AND and OR. It's something else, maybe better expressed as a short circuit expression. So he made this patch that is just replacing where he can logical expression to short circuit expression. And this is quite a simple one. So that brings us pretty much to where the spec is now. This is pretty much the complete spec. And you can see the changes that happened from the very first one to the last one. So we started with this. And we ended with, I believe this is it. Yes, we ended with this. This is the current specification text. So that was all done in the browser, because it was too hard to do it via slides. However, I have lots of slides for you folks. For example, we had Brendan Eich come onto this in stage 0 or stage 1 and say Nulliry is the wrong word. And we had lots of people being like, do we really need this thing? And we also, I'm going to skip that. And then other things happened. But one thing that I wanted to mention is this thing about syntax and semantics. We don't really come across these words very often in everyday speech. So another way to think of these two words is just to replace them with structure and meaning. The structure of the code and the meaning of the code. Like, what's the code doing and how should it be shaped? And then I'm just going to skip this stuff because we just covered that in the browser. But there are links to everything. And there's one last thing that I wanted to bring up. There was a bug in the early spec, and you can also now that you know how to read the specification text, you might be able to catch things like this and be like, oh, wait a second, we've got this this not nullish flag, and we can see that there's something going on there. So, and then all this stuff. OK, so let's talk about stage 3. We've got a complete spec text, and we've had designated reviewers sign off on the current spec text. And now, and also at this point, we've had all Ecma editors sign off on the spec text. So we can start implementing. How do we start? Well, I'm going to break this down into like some very high-level pieces of SpiderMonkey that this is going to be associated to. So on the syntax side, we've got something called the token stream and a parser. And I'm going to show how these two files sort of fit in, because those are the two that we're going to be looking at the most. And we've looked at this enough. So given a minimal program such as this, where we have function coalesce A, return A coalesce B, we now need to parse that. And how are we going to do that? And this is pretty standard stuff around compilers. So we take the text, and then we tokenize it, and we split it up into tokens. So we have a function token and an identifier, which is coalesce, left parentheses, another identifier A, comma, identifier B, etc. And what we're adding is we're adding this token, which is going to be named coalesce. But before we can do that, we need to make a fundamental change in how we're thinking about the question mark in SpiderMonkey. Because prior to this point, the question mark had been, which we call a hook in SpiderMonkey, it had been a single character token, which was used in the ternary operator. So we haven't implemented optional chaining yet. But now it's going to be used as a pair of tokens. And this is an implementation detail of how SpiderMonkey does it. So what we need to do is we need to delete it from a whole bunch of places where it's declared as a single token character. Here it's being declared inside of a comment. So this doesn't have an impact on the code, but it has an impact on how people understand what's going on. And then we delete it in a bunch of places in token stream. Finally, we update our token kind list. So we've got this big list of types that are called tokens, and we just need to add it in there and say what it looks like, which is a double question mark. And you can see that we've got other ones in here as well, such as logical or, logical and, etc. Finally, we need to update how this behavior works. Specifically, we've got a large case statement inside of this function called getToken. GetToken internal is an internal implementation of getToken. And what we do is if we hit a character that is a question mark, we're going to check if the next code unit is also a question mark. And if it is, we're going to say that the token that we're looking at is a coalesce token. Otherwise, we're looking at a hook token, and we're dealing with a conditional statement. OK, so we've got the tokens that we need. Now we can focus on building an AST. So again, we've got that list, and we're going to turn it into this data structure down here. There are two sides to it. One side is the arguments. The other side is the body of the function. We have the identifiers on one side, and then what we're doing with them in the body. In order to do that, we also need to update some more lists. So this first part where we're adding the token and like making it parsable is just a lot of list updating. So we implement it by adding a parse node kind called coalesce expression, which is of type list node. And then we add it to the parser's precedence list and say that it's of a lower precedence than or and. So you see here at number 2, we've got parse node kind coalesce. You'll also notice that I've updated the comment here while I was implementing it, because while I was implementing it, I discovered that the comments that existed were incomplete. They said that you only needed to update parse node, the parse node header and the token kind header. And actually, we also needed to update the bytecode emitter, because if we didn't do this, so this is just another list being updated in the same order as we've been updating the other lists. If we didn't do this, we had some really weird behavior. And what's happening here is I'm running the tests, and I'm trying to figure out if everything's working fine. I finished the implementation, and I'm like, everything's going to be great. And I'm running it, and I've got this really weird stuff. I'd been testing this all the time, and it had been working. But suddenly, now that I'm using other operators, it's failing. And then I started playing around with the operators, and I realized, oh my god, all of the other operators are broken. And observing it, I was like, OK, how are they broken? Well, they're broken in that they're now behaving off by 1. So the double equals was now behaving as, I I think it was the not equals 2. So if you don't update all of the places that it says to update, you will end up with the weirdest behavior in terms of what happens when you run the code. So finally, I want to just turn our attention to this function in parser in the parser file. It's called OR expression, but what it is it's our binary expression parser. And it handles everything from the OR expression all the way to every single binary operator that we've got. And when we look at it, just to point out a couple of key parts of this function so that we understand what happens later, we've got this unary expression, and what the unary expression is doing is it's taking anything that can be thought of as a unary, which includes anything in parentheses, and it's collapsing them into parse nodes. And for example, also a not is a unary expression. So if you've got bang and then a variable name or something else, it's going to collapse that into a single parse node. Then we've got this line, which is pulling a token from the token stream. And finally, we're associating that token to a parse node. OK, so this first pass, we're not going to do the behavior. We're just going to make sure that the syntax works as we expect. So we're going to pretend to be OR. And we're going to write a tiny bit of, just a tiny bit of bytecode in order to make that possible. Specifically, we're going to add the coalesce expression to the OR and AND definitions, the OR and AND case statements, so that it is emitted as a logical operator. And inside of emit logical, we are going to say that parse node kind is a valid operator to go into this function. Moz assert will throw if it gets something that is not valid. And we'll just say here in parentheses, it's a little hard to read, but we're basically saying just treat OR and coalesce the same. OK, let's run it. So I'm going to exit that. And we're going to go into here and run this function. So this would have thrown before, and now it's working. Cool, great. This doesn't work. We should be getting, the result here should be 0, but it's 2 because we've still got an OR operator there. So great, but you know, we've got the syntax working, right? Not quite. Hold your applause because things are going to get bad because this. Oh, well, I have to give you something other than that. This should throw. According to the specification, this should be throwing. And it's not, because we haven't implemented that specific thing about parentheses. So let's take a look at how that's going to be done. OK. So we have to come back to this issue and fix it. So let's think about how we're going to fix it. Before we fix it, let's think about how we fix it. And what we can come back to is this parser precedence list that we had before. One thing that you'll notice is that we're only interested in 3 operators: coalesce, OR, and AND. All of these other operators, we're not interested in. So how are we going to deal with, let's just go back to the code for a second. Let's say we've got more binary tokens going in there. Like, for example, these are separated by a +2 is equal to 4, something like this. And, we should still be throwing here in this case. But if we've got to interact with all of these other binary operators, how are we going to do that? Well, if we come back to it and we think, OK, we've got this folding going on. So actually, coalesce, OR, and AND are only interacting with one another. So if we come across an OR token, or we come across an AND, we can just record that we've seen it, and if we come across a coalesce, it will be valid for us to throw an error at that point, because we know that everything else has already been processed. And that's exactly what we did. So we just added an enum, and then this case statement. It's a little hard to read, but this case statement basically says, if you've got an AND or an OR token, and you haven't seen a coalesce expression yet, then you should say that you've seen an AND and an OR, and if you see a coalesce later, throw. And the same thing, but in reverse, happens for the coalesce expression. OK, let's run that. And, oh, not exit. No. Where am I? I am in the right place. There we go. OK, so let's try that again. We've got and, we've got the coalesce. And this doesn't work yet, but this should throw. Perfect, it is throwing. We have exactly what we want to happen. And if we do something like this, it still throws. Wonderful. So now you can clap. So basically, this was the syntax that we were told to implement. It has been implemented now. The syntax is covered. OK, let's move on to the semantics. Now, we are not going to... So I really wanted to cover everything, all the way from the beginning to the end of implementing the JIT. But we're not actually going to have time for that. So we're not going to cover the interpreter, and we're not going to cover the JITs. I highly recommend you check out Michael Seiboff's talk tomorrow, where he's going to be covering how that's done in a JSC, and that should be really interesting as well. And I have a patch for you to take a look at if you want to see how that's done in SpiderMonkey. And from this talk and from the next section of the talk, you should be able to follow it pretty closely. OK, implementing semantics. Here are the semantics. Let's read them again. Let's make sure we've got them in our head as we're implementing them. Let's start with the first instruction. Let the left reference be the result of evaluating coalesce expression head. Let the left value be the value that we retrieve from the left reference. If the left value is null or undefined, let the right reference branch, and let the right reference be the result of evaluating bitwise or expression, and then return the value from that reference. Otherwise, return the left value. Perfect. So we're going to be moving from the AST that we just saw to a proper bytecode implementation. In SpiderMonkey, we call this JS script. How does everybody here feel about assembly? Yeah, great. If you feel bad about assembly, what I've got on the screen here, don't be intimidated by it. It's a video game. It's called TIS 100, and it's how I learned assembly. The reviews on Steam are as follows. The assembly writing game you never knew you wanted. It'll give you a lot of practice with assembly. OK, so what we have in SpiderMonkey for the bytecode emitter is we've got a stack-based VM. What is a stack? And I'm just going to show you what happens in SpiderMonkey when you get a specific bytecode instruction, what we push onto the stack, and how things are manipulated on the stack given bytecode instructions. So we have an instruction, and we're going to push stuff. And as we do this, we're also going to define the behavior of the nullish coalescing operator. OK, here's our input. We've got A coalesces B. The string A is coalescing and with the string B. I'm not too sure how to put that into a sentence properly, actually. I realize now. And the first thing we're going to do is we're going to get the first argument. We're going to get 0 and push that onto the stack. So we have this string A on the stack. The next, oh, I'm sorry, I forgot my script. And then the next question we should ask is, how are we going to determine whether or not this thing is null or undefined? How are we going to determine that? Because we can't do it in C++. We actually need to do it in the bytecode instructions. The bytecode instructions are the things that are supposed to determine that. And those are like, well, you'll see what it's like. We can't really branch. You can't do an if this value in them as easily as you can in C++. But how can we do that? Well, at the moment, the bytecode has no understanding of null or undefined. We're going to do a really simplified example here, because what we can do to start with is we can say that anything that loosely equals null, which is more or less undefined, is going to be valid for our syntax. We're going to start with that. So how can we determine that A is not equal to null? Well, first, we need something to work with. And we can't use this value, because if we use this value A, we're going to consume it, as you see later. So we need to do something else. We need to duplicate it. And in SpiderMonkey, we've got this JS opcode called JS opdupe. And it's very simple. It takes the bytecode that's on the stack, on the top of the stack, and it duplicates it. So when we do JS opdupe, we have 2 A's on the stack. Next, we need to compare it to null, but we don't have null on the stack, so we have nothing to compare to. We can compare it to A again, but that's not what we want to do. So we need to push null onto the stack. To do that, we use JSOP null, and it pushes null onto the stack. There we go. After this, okay, so we've got what we need on the stack, but how do we access those top two values? How are we going to get those two things and say that they are equal or not? Well, we have an opcode for that as well, and I'm going to use not equal in this case. It's not the final implementation for specific reasons, but I'm not going to get into it. It's easier to understand it this way. It pops the top two values off the stack, and then it returns the result of comparing those two values. What does that look like? Well, suddenly we've got A and true on the stack. Okay, cool. Now what? Okay, so we've got true on the stack and we've got A on the stack. What are we going to do next? Finally, because we're going to have a branching happening here, we need to check what's happened from that evaluation. And then if it's true, we want to if it is a certain result, we want to jump to later in the byte code. Because we can't just branch the way that you do in C++. We have to jump to a specific address in order to continue with our evaluation. In this case, this is a really weird opcode. This is a bit of legacy. It's called if not equals. And what it does is it takes the top value off the stack. And it jumps depending on what that value is. Now, if not equals jumps if the top value on the stack is true. That might be a little bit counterintuitive. Interestingly, if equals jumps if the result on the top of the stack is false. So we have true on here. We want to jump. We just checked if null was not equal to A, and it's true that it's not equal to A. So we do want to jump when true. So we have jumped, and when we jump, we consume that. When we jump with if not equals, we're consuming that top, the top of the stack, and we're just left with A. And within the machine, we've got a stack counter that's checking where are we in terms of the stack depth. And we should be +1 for this evaluation. And we are +1 here. So we can continue on happily with whatever we want to do with the results of this evaluation. However, oh, and last thing. Wow, I'm sorry. The last thing that I wanted to mention is that in order to make that jump, we need to know where to jump to. But we don't know where to jump to until after we've gotten to the point that we need to jump to. So that seems like a bit of a dependency issue. And what we can do is this thing called patching. We can patch the jump target back, and we'll take its address and push it to where we wanted to have that jump address. So that's what's happening. OK, let's take a look at the other path that can be taken through the bytecode, which is if our left-hand side is null or undefined. If it's null or undefined, then our first couple of steps are going to be the same. We are going to get the first argument, which is a null. We're going to duplicate it, so we have two nulls. And then we're going to push another null on top of that, and we are going to check if they're not equal. Well, they are equal, so what we have on the stack is false. When we come to this point where we say we want to jump, we're not going to go anywhere, because if not equals jumps if true, and that was false. So, and the other thing is we've got this value on the stack called null, and we don't need null on the stack. In fact, if null is on the stack when we get to the end of this operation, then we're going to have our stack depth +2, and it should be +1. We only want one value coming out of this. So what we need to do is we need to get rid of it. For that, we have another JSOP code called JSOP pop, and we're going to pop it off the stack. Now we have an empty stack. And we can get the next value, which is going to be B. And we have this final instruction of the address of the jump, but we don't need to do anything with it, so it's kind of just there. It's there for when a different set of values comes through the pipeline. OK, that's it. Really simple. Let's actually implement it in SpiderMonkey on stage. And I've only been writing C++ for 2 weeks, so this is going to be a lot of fun. OK. So here we are. We have, I have here as comments a sort of a guiding thing to help us remember what we need to do. And I need to remember where I need to look, which is not at my screen, but elsewhere. So to start, we're going to do something that looks a little bit weird because it's SpiderMonkey, and SpiderMonkey is a little weird. We're going to say if, and everything's going to be if statements. If not, emit tree. So what did I just write? So emit tree is a complex function, but to make it very simple, this is essentially the same thing as we were doing in our stack that we were showing before, which is basically get 0. And what emit tree and all of the other emit statements in SpiderMonkey gives us back is true or false on whether or not things worked. But and this is going to be the pattern that we use throughout this demonstration. And we're going to, if we don't have that, then we're going to return false. Yeah. OK. We are also inside of a for loop, you'll notice here, which is, we're going to look at that a little bit later. For now, just imagine that we're parsing the immediate left-hand side plus, we're just parsing the left-hand side. But actually, if you have a chained expression, we need to recursively parse. OK, so we have the emit tree. And then next, we need to duplicate that. And I'm just going to reuse this. And instead of emit tree, now we need to directly emit a bytecode. How do we do that? Well, fortunately, we have something that allows us to do that. There's an emit 1. There's also an emit 2. But basically, what emit 1 does is it emits a single bytecode onto the. I guess it's also a stack, but basically the instruction set that we're building, we're emitting to that instruction set. And then we say JS op dupe, exactly the same one that we saw before. Then, if it's not null, oh, this is too soon. Not before it's not null. We first need to push JS op null onto the stack. And I can't spell. And while we're doing this, actually, let's do something. Let's keep track of where we are on the stack. Here we have an A. And here we will have another A. And here null. And then we check for equality. Or rather, not equality. We need to check for not equals. And once this happens, we have a Boolean on the stack. Then if it's not null, we want to jump. Now we need to change what we're doing a little bit. We're not just emitting bytecode onto the instruction set, but we actually need to say that, well, we're still emitting, but we want to say that once you hit this in the bytecode, if this condition is met, then we want to jump to a specific point. For that, we do emit jump. And emit jump takes 2 arguments. Again, we're using the exact same bytecodes that I've already shown you. And now I'm going to pass a reference to this thing called jump. You might notice up here that we've got jump list jump. And this is basically saying that we will have a variable of type jump list called jump. And we're passing a reference of it into this emit jump function. When this happens, we actually pop the bool off the top of the stack. So it's no longer there. And let's follow the happy path and continue that. But that jump hasn't, we need to define it somehow. So we need to patch it so that we can define it. And what we can do is the same, pretty much the same pattern as what we've been doing before, which is and this just takes the jump list as a value. And that will update this bytecode that we're emitting here. OK, so that's the happy path. We just covered the happy path that we saw in the slides. And now let's cover the other path, which is if we do have null or undefined. So here, what am I doing? We need to first pop. And again, we're doing just the same thing as we did before, passing instructions up. And after that, we want to get 1 but we're in a for loop, so we actually don't need to do it here, because we're going to go back up to the top here, and we're going to emit here again the next value that's coming through. However, at some point we're going to get to the end of what we need to emit, and we need to break out of this loop. As you can see, there's no break condition in this for loop, so we're going to add that here. So we have a pointer that's pn next. And break if that's the case. That's it. That's the whole thing. So let's run it. Well, first let's compile it. Don't do that. Right, so this is the fastest bit of the compilation of the whole thing that I could show you, so that's why I'm doing it live. But I just wanted to talk to you a little bit about C++. So when I started on SpiderMonkey, I started 2 weeks ago, and I hadn't written that much C++, but if you're nervous about C++, don't be. It wasn't so bad. I ended up doing just fine on it. I'll continue this after we do this bit. So now let's run and see if we've got the correct behavior that we expected. So let's say 1, 2. We've got a 1. That's the correct thing that we wanted to get. I'm going to give that a little bit more space. And now let's see if we can pass false. And we should get false here. And we've got false. The bytecode is working. Fantastic. All right. Now, does it also work for null? Oh, I did something wrong. What did I do wrong? Huh. I have no idea. I practiced this and everything. OK, well, we've got a few minutes, so let's see if I can figure it out. If it's not equal, jump, duplicate null, not equal. Here we are. OK, I put in the wrong bytecode there. So let's build it again. And now it should work, because I put in the wrong bytecode. Ow. So yeah, I highly encourage to explore with, like, if you don't feel super confident with working in a different language, just try it out. It's gonna be great. All right, here we go. So let's give that a bit more room again. And 1, 2, that works. 0 works. And now the moment of truth. I have no idea why it's not working right now. Did I not save it? Well, if this doesn't work, I'm just going to show you the final version of it, and we'll just go on. Live coding. That's always a disaster. OK, cool. I have no idea. Let's just move on. OK. Moving on. Let's take a look at what we need to do next. Assuming this had worked, which is currently not working, would everything be fine? Well, actually, it wouldn't. Where's my mouse? There it is. Specifically, the problem is that we do have a full parse going on, and we get all the way down to the bytecode. But the problem is, and I'm just going to do a quick aside here, one thing that's really amazing about the web is backwards compatibility. And I want to show this really cool project by Diana Smith, which is CSS Francine. And what this is she made this image of a woman that renders really well on Chrome. And she said, I didn't really optimize this for other browsers, but it makes a really great example of like how backwards compatibility, like, on the far side there, you'll see that you can actually see sort of an image of a woman. It's just the further back in time, that browser over there is Netscape. The further back in time you go in browsers, like the more avant-garde the art gets. So that's like really cool, but how does it impact our situation right now? So that's the end of that aside. Now, I want to bring your attention to something that some of you may have come across while programming for the web, and some of you may have not. It's called document.all. And why is this an issue? So if we jump into the browser Let me make it. Oh, this is as big as it's going to get. Oh, no. OK. Wait, maybe I can. Oof. That is as big as that gets. Damn. So it's really tiny, but try this on your browsers. Type in document.all, and you'll get something called an HTML all collection. Now, this shouldn't be affecting us for undefined and null, right? Because we're testing against null and undefined. So why would this be a problem, right? Well, if you type of, you're going to get back undefined. Now, I know everybody in the back can't see that, but it comes back as undefined. Why is this? Well, it comes back to backwards compatibility. The problem is that Internet Explorer implemented this thing called document.all, and the other browsers hadn't. So people started testing for browsers using document.all. However, some websites didn't do that, and they utilized document.all, and it would break in Firefox. So Firefox had to implement document.all, but it also had to make it appear as though it was undefined when people tried to test for it, using it, like trying to check what the type was. So that's why in Firefox and many other browsers, we have undefined coming back when you have document.all in a given expression. However, this is it's really just debt that we need to deal with. It's not standardized, it's just something that we have to deal with. But we don't want to deal with it going into the future. And since Nullish Coalescing doesn't specify that how we should behave with document.all, we should treat document.all as though it was a normal object, and actually it shouldn't be treated as undefined, even though it comes back as type of undefined. Which means our initial implementation, where we used loose equality to null, does not work in this case. We need to use strict equality. So let's implement that, and let's see if it actually works this time. And I'm going to try and see if I can tell what I did wrong. No, I'm not. No, it's definitely there. I have no idea what I did wrong. Anyway, it might not work still, but we can see the working version later. So now we're going to have to add a lot of extra stuff. Specifically, we're going to have to put undefined onto the stack, and we're going to have to do the equality check for undefined, and then we're going to if that's not true, then we're going to have to push null onto the stack and check if that's equal, and this is a lot of extra bytecode, and actually we have something called not defined. We have this function called emit push or not undefined, and if we sit down and we read this bytecode, we see that it emits duplication, then it emits undefined, then it emits strict not equals. Well, this is basically exactly what we need, right? We don't need to do any other stuff. We can just reuse this set of instructions. OK, so back to our function. So I just got rid of the custom code that I'd written, the custom bytecode that I was emitting, and I'm going to just replace all of that. And say emit push not undefined. And that doesn't need the expression. OK, cool. All right, so I have my doubts about this actually working in the end, but let's try it. Let's see if it works. And we'll be there in a second. And that'll be the full implementation with some bugs. OK, let's try this. Still not working. That's a shame. That's really a shame. I'm sorry that I can't figure out what's wrong with this. But unfortunately, the time is running down, so I'm just going to continue with the talk. And I will share with you a working version of the implementation that you can run yourself. One thing that I want to show you before I move on is something pretty neat in our tools for SpiderMonkey. Specifically, what you can do is you can create a function with a name. And then you can disassemble it in order to see the bytecode that we're working with. So I missed my... See, I definitely did something wrong, but I'm not sure what, because that's not what the bytecode should look like. But we can disassemble the bytecode. OK, moving on. So we covered that. This is my face, especially right now, because I just did this in front of I don't know how many people, and it didn't work. But the appropriate solution to this, the final solution we ended up with, was actually a new bytecode called JS op coalesce. And what we end up with is a much simpler bytecode coming out than the bytecode when we emit it using the if not undefined or null instruction set is actually very messy, and there's a lot in it. But what we end up with JS op coalesce is much simpler. We just have a jump target that we go to after we coalesce, and it's really clear. So finally, what we're going to do is we're going to pull in the tests. And what we do on SpiderMonkey is we just pull the test 262 tests directly, and then we run them. I also included the tests from JSC in this case, so we have some extra tests because it was more thoroughly tested in JSC. And that's it. That's it. So we've got the runtime semantics not working, but you know, you can try it. You know, you should try it at home. You now know how to do the whole thing. Just pull Firefox and try building it yourself and see if you can get it running, because I clearly didn't. And that's it. Semantics are covered. OK, let's review what we covered. We had the 4 stages, which we went through. Someone has an idea, idea is presented, etc. And then we covered the difference between syntax and semantics and how that looks in the spec text. We took a look at a minimal program. We built the AST. We emitted the incorrect bytecode. And then we had the full parse. Fantastic. Are we done? What do you folks think? No, we're not done. That's correct. Stage 4 has not yet been reached, and we are going to stage 4 in December. So next month, keep your eyes out on the TC39 repositories and check it out. You can see what happens just in a couple of weeks. And thanks. That's it for me. If you're wondering what this fruit is, that's the name.
Very impressive to see all these things behind the scenes and all happening. We have just 1 minute left. Oh, but I think that if you could join me just for a moment, I think somebody must have solved it, by the way. Somebody must have found the bug. So we have Alexander, who's been really apparently passionate about that. He said, looks like one of the expressions must be with the exclamation mark.
Oh my God. Really? Should we test it? Yeah, OK, let's take a look. If that's it, then I'll just try some.
This is a very short Q&A here.
You can keep asking questions. I'm just going to see if...
actually, so there was a very nice question from Vlad, who asked, so the stage 0 was committed as idea in 2017, many years ago now. How long did it take to implement? And how long does it take them to implement in general, on average?
It took me 1 week to implement it. And that's because I didn't know any C++ and I'd never touched SpiderMonkey before.
OK.
But it did take 2 years to come to the final specification, because we're not working on the specs continuously, and like sometimes people come on, sometimes people come off. Oh my God! I think that person was right. I missed a knot.
Let's see if it works. Totally behind the.
Oh.
Segmentation folder. I haven't seen that.
Well, it's basically like undefined is not a function, right?
Yeah. Well, that's okay, I guess. Well, we can always do it in our spare time.
Yeah, try it out. It'll be fun.
Yeah, that sounds about right. So I think we're totally out of time at this point.
Yep.
Maybe just one thing from my side before we wrap up. So if somebody wants to follow up and track like what's happening in SpiderMonkey in terms of developments, and also maybe what you have on your plate coming up next, what would be a good place to start? And what are you most excited about of what's coming up next in JavaScript?
In JavaScript, OK, that's easier to answer. I'm most excited about the pattern matching proposal. I think that's really exciting. That fills a space that I think could really be improved. And to follow what's going on next, the bug tracker is the best place to do it. So we've got a SpiderMonkey component in Bugzilla, and that's the best place to watch what's going to happen next.
Okay.